Hello, we are Team Sun Running with the Dawgs. In this video, we'll cover our solution to the SunRun panel installation process for the Simio student competition. From the data provided, we used key variables such as permit submitted date, latitude and longitude locations, and standard install hours. These variables were adjusted in order to use JUMP and determine the proper distributions. We also utilized Excel in order to determine the proper mix for the different panel types, which we specified as small, typical, and complex. We counted the number of panel jobs in each type and divided this by the total number of panel jobs. In addition, we found the other mixes for number of inverter jobs, bright box jobs, and upgrades by each panel type.
This is an example of one of the distributions resulting from JUMP. We initially converted all of the dates to time between dates excluding weekends. Once these numbers were adjusted in Excel, they were input into JUMP to find the best distribution for our inter-arrival time in the source. Our initial inter-arrival time was a Johnson 2 distribution. However, we found that this distribution did not accurately adjust to prevent non-negative values. We used JUMP again and selected an exponential distribution which better fit our model. Our model has 3 entity types for each job. They arrive from the permit source and then travel to the warehouse server where the truck loading time is simulated. From the output node, box trucks transport the panels to the appropriate job sites where the panels are installed by the workers. Once service is completed, the panels are sent to the sink.
The table on the left displays the sequence for entity types, more specifically the route each entity takes when they are created. The entities of each panel type are generated from the mix specified in the table on the right. The mix was calculated by determining the probability of occurrence for each job type in the given Excel data. Each entity has an associated processing time for their job type. This was calculated by averaging the standard work hours per job site.
This is a picture of our employee work schedules. There are different schedules for Monday, Wednesday, Friday versus Tuesday, Thursday, and Saturday. This is due to an assumption we made that overtime only occurs on Monday, Wednesday, Friday, and Saturday for a set number of hours for consistency. Within the work schedule, all workers work from 9 to 5 on Monday through Friday, while also working an extra hour on Monday, Wednesday, and Friday. All workers are also present on Saturday for 4 hours. A status plot was made in order to track the average number and system of each of the 3 panel types. We used this to ensure that the model goes to steady state and to evaluate a warm-up period for our experiments, which we found to be 26 weeks. We incorporated status labels into our design in order to determine if the workers were being seized appropriately and following their work schedules. These were important verification and validation techniques we employed to ensure accuracy in our models. We organized our process into several different categories such as assigns, electricians, install blocks, releases, seizes, and routing. We created a few model entity states in order to track certain identifiers such as bright box panels, upgrades, and the number of inverters for each job. As shown above, we had 3 processes designed to assign the model entity states. The processes used aside statements and respective probabilities to assign each type based on a mix created from the dataset provided.
For each of the panel types, we created individual seize and release statements which were called on in an overall seize and release process pictured here. On the left, we see a complex panel seize of vehicle and resource workers. In the process above this, we have combined all 3 processes for small, typical, and complex panels in a couple of decides in order to select the correct seize process. Likewise, the right side of the screen displays a similar process for releasing these resources. In order to call on electricians at the appropriate time, we created this process to delay for the length of time necessary for the majority of each job to be completed. After this delay, we created a dummy entity to seize an electrician and an employee car. We then set the appropriate row for the processing time in the previous panel table. These dummy entities are then transferred to the appropriate location.
This is the process used to model the install blockage. As shown above, the process was implemented to use a probabilistic decide which will then delay 5% of all jobs for the amount of time given in the problem statement. We also used 2 more delays to represent the lost travel time and the truck unload time for that given day. The process is then attached to the output node of the warehouse.
In the second model, we used a pre-equipment kit that contains solar panels, inverters, mounting rails, and brackets. The main difference in our second model was adding 3 more entities that represented the equipment kit associated with small, typical, or complex jobs. These entity types were routed from the source to the pod production server, then to their respective install sites. These equipment containers are pre-positioned at homes 2 to 3 days in advance, which is modeled in the service time.
This is the sequence for each panel in the pod system. Included is a small, typical, and complex panel carried over from the first model. In this model, there is now an additional small, typical, and complex pod for each job site. They arrive based on their original mix probability from the baseline model, which is multiplied by either 0.15 or 0.85. This is because 15% of homes take the original baseline route. The 0.85 represents the 85% of entities that take the new routes with the pod system.
Each of our entity types have different colors so that we are able to visually determine which entity is traveling to each destination. This was very important in our second model to verify that the pod panel types and regular panel types were traveling to the correct stations, either the warehouse or pod production server. Our vehicles have different colors to differentiate between idle, busy, and transporting to validate that they are correctly taking entities to their install servers.
For our second model, one of the major differences was a pod delay and execute process. This process executes a seize resource and vehicle, electrician seize, and install block process. All of these processes were duplicated and updated for the implementation of the pod, and this process was attached in processing for the pod production server. In the case of using pods, we did not seize a box truck or equipment truck as we assumed that all materials necessary were in the pod, and only workers and employee cars needed to transport to the install sites.
Within each respective model, we created 8 experiments to model an increase in demand, bright box demand, and solar panel upgrade demand. We created experiments for regular demand and from a 10% to a 30% demand increase. To account for these increases in demand, we made a reference property for the in-arrival time, and within the distribution, divided the parameter value by its respective increase. For example, a 10% demand increase gives the in-arrival time of random.exponential 0.37898 divided by 1.1. Next, we made an experiment to monitor a rise in bright box demand in typical and complex jobs and modeled this by multiplying the probability of a bright box in typical and complex jobs by 1.25. Finally, we made an experiment to monitor a rise in solar panel upgrade demand and modeled this by multiplying the probability of an upgrade by 1.2. Within all these experiments, we then utilized Simio OptQuest to minimize the total cost by finding the optimal crew sizes for small, typical, and complex jobs. This optimization was done according to constraints that states the minimum and maximum crew sizes given in the problem statement.
These are some of the most significant statistics when comparing the effectiveness in the baseline and the pod model. The baseline model is represented by significantly lower monthly costs, while the average installations per month is similar between the two scenarios. This means that the baseline pod system is installing the same amount of panels while doing this at a significantly lower cost. This equates to a higher profit and revenue for SunRun. All of the experiments that were previously mentioned here are shown. Through the data, we see this as a demand increases the total cost increase in the pod model, and the average installation per month increases for both models. These values intuitively make sense as we would expect the average number of panels installed per month to increase with an increase in demand.
Pictured above is a histogram for the two best scenarios of the baseline model and the pod model. The box on the histogram represents the confidence interval for each model. Through evaluation, we see that the baseline model on the left has a much tighter confidence interval, and therefore we are more confident in these results. This reinforces our recommendation that using the baseline model is a better choice for SunRun. Based on our two models and tracking the appropriate performance metrics, we have 3 main recommendations for SunRun. The first recommendation is about the pod system. Through our model and the evaluation of worker utilizations, we found that in order to implement the scenario, SunRun would need to hire more workers, as well as purchasing additional cars used to transport the workers in order to make the system effective. The next recommendation focuses on the optimal crew sizes. Using OptQuest in Simio throughout both models, we found the optimal crew size to reduce total cost was 4 for small installs, 5 for typical installs, and 10 for complex installs. We recommend that SunRun implement some sort of policy or strategy in order to focus on using these optimal crew sizes as much as possible. Finally, in comparison of the two scenarios, we recommend SunRun stick with the original baseline process rather than transferring over to the pod process. The pod process is a smart and creative idea, but since 15% of homes cannot use this, our model found it would be easier and more cost-effective to continue using the baseline process. While analyzing both scenarios and the metrics of total cost and total installed panels, we found the baseline process installed more panels at a lower total cost, meaning the revenue from the baseline model would be much higher.
Thank you for your time.